Hi everyone. I wanted to take a couple of minutes and go over this handout on polar regions. So in part one here we began by shading in some regions of the plane that are determined by various rectangular inequalities. So here are the set of points in the plane whose x-coordinates are between 1 and 3. Here are the points in the plane whose y-coordinates are between -4 and -2. And then here we have a double inequality, a dual set of restrictions on both the x-coordinate and the y-coordinate. And this is essentially the intersection of these two regions. So these are inequalities in rectangular coordinates. And the key idea here is understanding what the most basic fundamental equations and inequalities in a coordinate system determine and specify. And so here in rectangular, these basic inequalities determine essentially rectangular regions. This is an infinite rectangle, this is an infinite rectangle. Their intersection is this little square here, but you could imagine with different parameters it could be a little rectangle. So we want to understand what the fundamental inequalities in polar determine in terms of regions. So here we want all of the points whose r coordinate is between 1 and 3. Now r is the distance to the pole. So this means we want all points in the plane whose distance to the pole is between 1 and 3 units. So here's the circle r equals 1, and here's the circle r equals 3, and we want all of the points between those two circles. Now, what does this basic equation or inequality in polar determine? So here we want all of the points whose theta coordinate is between pi over 4 and pi over 2. So here's theta equals pi over 4, and here's theta equals pi over 2. And so that would give us all of these points in the polar plane. But we have to remember that the distance from the pole r is a directed distance, which means it could be negative. So you could be pointing in this direction, but go backward. So we actually want all of these points as well. So this inequality determines this kind of region. This inequality in R determines an annular region. And so if we have like a pair of inequalities that are working together, that would give us something like this. So again, the key idea here is understanding what the most basic inequalities in each coordinate system determine. And so if we want to know what regions are simple to express in rectangular, well, it's going to be some combination of these things, and they're going to be rectangles. The regions that are simple to express in polar are going to be regions like this, little sectors of annuluses or circles. Now, the bigger question for us is, what does area under a curve mean in polar? So in rectangular, we have a pretty good idea of what area under a curve is. Here's the curve. Under means between the curve and the x-axis. So here's the x-axis. We want to go from 0 to 1. And this is the area under the curve, y equals f of x, from x equals 0 to x equals 1. In polar, area under the curve means something very different, though. So here we want to think about the area under f of theta from theta equals 0 to theta equals 1. Well, here is theta equals 0. Now, remember, theta is in radians. 1 radian is about 57 degrees. And so 1 radian is like this. This is theta equals 1. So we want the region between these two rays right here. And we want the region under f of theta. But under f of theta really means r between 0 and theta. And so we want all of the area that radiates from the pole like this. So this is the area under f of theta in polar. So it's a very different conception of area. So when we go to compute this area under a curve, say via integration, we have to take a much different approach than we did in rectangular coordinates.